Hey there, you're on Vectorly, and today it's all about work power energy. This is the second video of work power energy. Okay, now what is why there is a use of work power energy in our JEE problems? The main thing is everywhere a work power energy problem can be solved using Newton's laws of motion too, but it requires complex analysis because when a body is sliding in an wedge, you can use Newton's laws of motion easily because the angle, you know the angle theta and the forces acting at each and every point. But if a particular body is moving in a curved surface, we don't know the angle made by the tangent at each and every point. So work power energy plays a major role at this particular point. Most of the questions of work power energy can be solved using Newton's laws of motion too, but it requires a complex thinking. So work power energy simplifies mechanics. Okay. We often think of work as just force into displacement, but in physics, it's the bridge between force and energy. It tells us how motion transforms, how potential turns into kinetic and sometimes disappears as heat. Let's move towards the first question. Consider a fixed hemispherical bowl of radius r with its opening horizontal. One end of a light rod of length L equal to r is hinged at a point A on the brim of the bowl. A small bead of mass m is attached at the other end of the rod. Initially, the bead is held at a point B, also on the brim, and then released. Find the tensile force in the rod when the bead passes the lowest position. Acceleration of free fall is g. Now, uh, A and B are in the same horizontal plane. That is the top brim of the hemispherical ball. Okay, let's imagine this setup or redraw the setup here. Okay, now I am drawing the top view. Okay, in this top view, or point A is somewhere here, and let this be the center of the hemispherical ball. Okay, now what happens is point B is around here. Okay, now I am connecting A and B. We are using a rod, and these are all the radius. So this is R, this is R, because A and B are in the periphery. Okay, now this is the rod, and this is also a length of r. So triangle ABC is an equilateral triangle, so the angle is 60 degrees. Okay, now let's think about how the motion of the ball B would be. Okay, it's a bead, actually a bead of mass small m. This is a bead of mass small m. Okay, now let's analyze the motion. B is always in the surface of a sphere with radius r and center A, correct? So B always lies on the sphere of center R, sorry, center A, and radius is capital R. Okay. Also, B always will try to remain in contact with the hemispherical bowl because of the gravity. Okay. So B will be on the surface of bowl 2. Okay. So if you analyze the motion, these two are spheres, right? This is also a sphere, and this is a part of the sphere. So the intersection would be an hemisphere in the vertical plane. Okay, if you imagine, if I see from the side, the intersection would be a hemisphere. Okay, actually, I not a hemisphere. Sorry, it's a semicircle. Semicircle out here. Okay, and I'm just drawing a circle, and a part of it is what the motion would be. Okay, now if you see from sidewards, what is happening is initial position, and this would be the final position. Okay, now what happens is this is the center, this from center, okay, this is the perpendicular distance from center which I'm speaking about, okay, and this is the total horizontal distance it traveled. Now what is happening is, at the lowermost point, I'm speaking about the lowermost point, I'm freeing on the side, this is point A, okay, and this is the center C. At the lowermost point the ball will be light here, okay. Now what happens is, this is distance r, this is distance r, and this is also distance r, okay. The equilateral triangle remains the same, okay, and this simply the equilateral triangle is rotating about the axis AC. That is what happening in this situation, and this angle is 60 degrees, so this is 60, and this is an equilateral triangle, so this is r by 2 out here, okay. Now this particular ball or bead is rotating in a vertical circle with this point as center, the midpoint of A and C as center, okay. Since this is an equilateral triangle, we have symmetry out here, so this is the center, okay. Now what happens is, here tension T acts, okay, and normal reaction would act in this direction, that is, normal reaction would act in the direction of, if this is the surface perpendicular to it, okay, normal reaction will act in this direction, not perpendicular to the tangent. So it will be along the radial line connecting this point to C, so it will be in this direction. So this angle is 30 degrees and this also 30 degrees, and white mg acts downwards. Now if you see properly, there is no motion, the motion is completely a circular motion, vertical direction, so there should be no force in this direction. So net force in this direction is 0. So component of t in this direction and n in this direction should be 0, which is nothing but t sine 30 equal to n sine 30. So first thing we are going to conclude is t equal to n, okay. And the next point is, uh, what about the centripetal force, okay. The centripetal force is nothing but component of t in this direction and normal reaction in this direction, that is t cos 30 degree plus n cos 30 degree. As t and n are equal, what am I going to write is centripetal force is t cos 30 degree, which is t root 3 by 2 plus n cos 30 degree, n root 3 by 2. So total we get t root 3, okay, and minus mg is nothing but mv square by, I want this particular height, correct. This is the center and this is the radius of the circle about which it is rotating. Now this is r and this would be r sine 60, which is r root 3 by 2. So t root 3 minus mg is equal to mv square by r root 3 by 2. Now I want a relation between v square and r because I want the answer of t in terms of mg, okay. So I have to eliminate v square and r. So now comes the role of work power energy. We are using conservation of mechanical energy. Initially the only energy it has was potential energy, okay. The initial energy was potential energy. So initially the only energy it had was potential energy, which is nothing but mg into the height from, I'm making this as my reference, okay. When this is my reference, this particular height is r root 3 by 2 as we found it here. So mg into r root 3 by 2 was my initial potential energy. And what is my final energy? Final energy is, for final potential energy 0. Finally it's converted completely into a kinetic energy. So mg r root 3 by 2 is nothing but half m into v square, okay. So at that particular point v square is nothing but g r root 3. So what I get is t root 3 minus mg is nothing but mg into 2. So what I get is t root 3 is equal to 3 mg and t is nothing but root 3 mg. this question cannot be easily solved using Newton's laws of motion, because at each and every point you have to draw this, and the normal reaction would be pointing in this radial vector and just along this. This is also easy. In this particular case, it might be easy because always the normal reaction makes 30° with this particular vector, so it might be easy. But anyway, upon solving, you require this relation between v square and r, where work power energy helps us.
Let's go to question number 2. What this question tells us, you just pause this video and read this question. Okay. Now, what this question actually tells us, let's consider the case. You have this particular rod in which a sleeve of mass capital M is given an horizontal force of F. Okay. Now, there is a string attached to it. Okay. At the midpoint of the string, you are hanging a block of mass small m, and this makes an angle of theta at each and every position. The initial angle is theta 1 and the final angle is theta 2. Okay, at initial position, both are at rest, and we are just starting to apply the force F. Okay, now if you, they are asking the final speed of the cord, just they are calling as cord or sleeve, at when the angle is theta 2. Okay, you can use both work power energy and Newton's laws of motion method, but in Newton's laws of motion method you get it would be complex because the angle theta is changing, and the relation between the acceleration of the cord and acceleration of the block gets changing because it will be in terms of theta, and the theta is also changing. You have to find another relation for theta and it will become much complex. So we are going with work power energy. Okay, the first is, this would displace a vertical displacement of, vertically it will move y, and this would horizontally it will move a distance of x. Okay, now, so what is the work done? Net work done is nothing but, this is doing a positive work, correct? So which is f into x, as both are in the same direction, cos 0, and weight mg is acting downwards, so this is a negative work, so minus mg into y. Okay, net work done, it's nothing but the change in kinetic energy, right? So Fx minus mgy is nothing but the kinetic energy. Okay, this is the law of conservation of energy. So let the velocity of this be v1 and v2 in this direction. Okay, so the half capital M into v1 square plus half small m into v2 square is what the total energy. Correct. Now we need a relation between v1 and v2. Exactly, v2 in terms of v1. Okay, so how are we going to do it? We know that the constraint comes here. Okay, this is L by 2 and this is also L by 2 because this is a midpoint, and this will also be a 90° perpendicular at this particular point. Okay, because this is an isosceles triangle, summation t vector, the dot v vector would be 0. Correct. So here I get some tension T, here too I get some tension T, and here too I get the same tension T because they all belong to the same thread. So uh, this V1 and V2 are at the angle theta 2. So this is supposed to be theta 2. So T cos theta 2 into V1, but they both are in opposite direction. So negative sign plus here T sine theta, but there are two T's. So 2T sine theta 2 into V2 is 0. So what I get is, I have to write V2 as function of V1. So V2 is nothing but V1 cot theta 2 whole divided by 2. This is the relation of relation 1. Now what happens is I need to find the x2, right? What is x? The initially, what is this distance? The total distance of initially the total distance is, that is this part, from this part to this part is L cos theta, right? And finally, initially it's L cos theta 1, finally it's L cos theta 2. So total, the displacement x is nothing but FL into cos theta 2 minus cos theta 1. Okay, minus what is mg into y? So y is nothing but L by 2 sin theta 1 minus L by 2 sin theta 2. Okay, which is minus mg into what is the distance y, sin theta 1 minus sin theta 2 into L. Okay, this is what the work done. Now let's apply all this is 2. Let's apply these two in this equation. So FL into cos theta 2 minus cos theta 1 minus mg into L into this L by 2, actually L by 2 into sin theta 1 minus sin theta 2, which is half capital M V1 square plus half small m V2 square, which is nothing but V1 square by 4 into cot square theta 2. From this equation, you can find V1 because all the remaining values are given. Okay, I'm not going to simplify from this part. You just do it. I want you to think about this solution via Newton's laws of motion. Just analyze the motion. If you have any doubts, just comment it down. I will also post by solving it with NLM. Okay. Question number 3. Two small identical discs, each of mass 1 kg, placed on a frictionless horizontal floor, are connected by a light inextensible cord of length 1 meter. Now the midpoint of the cord is pulled perpendicular to the line joining centers of the discs by a constant force F, which is 2 Newton. What is the velocity of approach of the disk? First, let's analyze this situation. Okay. Now, what happens is this particular system is given a force F at the midpoint. Now, let's see from the center of mass frame. Okay, our center of mass would be at this position because this is the midpoint. Okay, we have center of mass C over here. Now, what is the acceleration of center of mass first? Acceleration of center of mass is nothing but force F is acting, and total mass is 2m. Okay, now in this direction, so which is I cap. Now, with center of mass frame of reference, if we keep this as frame of reference, we will give pseudo accelerations for these two bodies in this direction. F pseudo. Okay. What about what are the F pseudo force values? That would be F by 2 in for each body because the acceleration is F by 2m and each body mass is m. So in this direction. But will this F by 2 cause any work? Let's calculate. Work done by pseudo force. Okay. I'm just writing as pseudo force. With the center of mass as frame, what is the final position? The final position of the bodies would be around just before collision. It will be around this way, correct? And F acting here and at particular point it would be L by 2 just before collision. So to calculate the velocity of approach, this distance would be L by 2. Okay, just before collision, I'm just considering it. Okay, the center of mass is not displaced. Okay, the only up with center of mass frame of reference, the whole thing, the two discs move in only in this direction, that is vertical direction, no horizontal direction. So the work done by pseudo force would be zero. Okay. So what which energy is converted into kinetic energy? So which energy gets transformed into kinetic energy? There is a question which arises here. But this is what the force F does. The work done by force F is nothing but F into L by 2, because initially it was in the center of mass and it moves, the point of application of force moves L by 2 distance. So the work done by the force is F into L by 2, which is the extra energy which provides to these two disks to obtain kinetic energy. Both are symmetric, so I'm just putting it V of the kinetic energy of the system. As the result is each body mv square into 2. Okay, this is the kinetic energy of the system. You see, you can also say that there is no force in vertical direction, then how there is a vertically induced velocity, but the net velocity of this is zero because both are v in opposite direction. Okay, so this kinetic energy is nothing but given by the work done by force F. Okay, so mv square is nothing but F into L by 2. Okay, so what is the velocity v? V is nothing but under root Fl by 2m. Now the velocity of approach is just twice of it, because I'm keep velocity of approach is nothing but keeping one body as at rest, considering one body is at rest. With what velocity the other body is approaching. So it is nothing but twice of it. So velocity of approach is nothing but under root 2Fl by m. Now this question will get complicated if we are not considering the center of mass as a frame. Okay, so we have to consider the center of mass as the frame to make it easier. Try doing it without using the center of mass as frame and without using the conservation of energy. We are the force. If you are trying to doing it, you have to take angle theta, and this case would be much more complicated because the vertical acceleration is nothing but that there will be tension force acting over here, and the component of tension force will keep on changing, and that causes the vertical acceleration. So you have to integrate and all that. So NLM takes much longer procedure to find the same answer. Question number 4. A horizontal frictionless thin rod wearing a sleeve of mass m is being rotated at a constant angular velocity omega about a stationary vertical axis through one of its ends. The sleeve is held stationary with respect to the rod at a distance r equal to r1 from the axis with the help of a light cord as shown in the figure. At some instant of time, the cord is cut. Find the work done by external agency in maintaining the angular velocity of the rod constant until the sleeve slides to the distance r equal to r2. Now, what actually happens here is this particular rod is rotating with an angular velocity of omega, a constant angular velocity. But if in reality, if something rotates, in reality, consider there is no cord kind of thing. So it will try to move outwards because of centrifugal force. Okay, now we are having a cord which tied to the center, so it remains at rest. Okay, so centrifugal force is compensated by the tension in the cord. Now what are we going to do is just cut this cord, so automatically it will move some distance along the length of the rod, right? So that distance is nothing but r2 minus r1. Okay, now we have to analyze this, and there must be an external agency, right, which maintains the angular velocity omega. Else, upon moving from this position to that position, there is an increase in energy. So automatically omega will reduce. So in order to compensate it, we need some external work. Okay, we have to find that external work. So the final external work is nothing but the change in energy. The change in mechanical energy of the system, it should be supplied. Okay, So let's calculate. This is frictionless, so we don't have the will and friction, which converts the whole mechanical energy into heat. Now, what happens is, let's calculate what is the initial energy. Energy initial. If you see the initial energy, what happens is, it is, let's consider the mass as m, and as the omega is not changing, the kinetic energy of the rod is not changing, so we are not going to consider the whole system. The initial energy of this particular sleeve is what we are going to consider. The initial, it's completely rotational kinetic energy, and there is no translation along the rod too at initial case. So it's nothing but half m into r square, which is nothing but I at this case into omega squared. Half I omega square is the initial energy. So what is the initial energy at the final point? At the final point also we have the same rotational energy. This is R1 initially, rotational kinetic energy in same omega square. With that, we have another translational kinetic energy. If you see here, if this is the rod, the sleeve would have a velocity v along the rod. Okay, if we are seeing with respect to the rod, okay, the rotating rod in the rotating frame. So it will have a translation kinetic energy too, which is half m v square. But which is responsible for this translational kinetic energy or this velocity, which is the centrifugal force. If you are keeping with this frame, you have to consider the forces centrifugal force and Coriolis's force. So if you have, if you know the concept of these two forces, you can apply NLM to obtain the same answer without work power energy too. But if you want in that method, just comment it down, I will do it, because we have to introduce the concept of Coriolis's force over here. Now let's consider the centrifugal force and calculate the velocity v. So the velocity v is given by the centrifugal force. The centrifugal force is the acceleration due to centrifugal force, which is v into dv by dr is nothing but v square by r. Okay. Now what happens is v is changing, but the omega is constant. So I can write as omega square r. So v dv is omega square r dr. So upon integrating both sides, integral v dv is equal to integral of omega square r dr. Now r is moving from r1 to r2. Okay. The limits are important in integration. The initial velocity is nothing but 0 and final velocity v is what we want. Okay. This gives v square by 2 at 0 and v, and omega square r square by 2 from r1 to r2. Okay. So this implies v square is nothing but omega square, this is r actually, into r2 square minus r1 square. Okay. So I have to substitute this value out here. So what is the energy final? Energy final is nothing but half m r2 square omega square plus half m omega square r2 square minus r1 square. So the energy final is half m r2 square. Okay, no. The energy final is, okay, half m omega square into 2 r2 square minus r1 square. Okay. So the total change in energy, this delta E is nothing but E final minus E initial. Correct. Because the work is being done by the external force on the system. So which is half m omega square into 2 r2 square minus r1 square minus half m omega square r1 square. So what I get is m omega square into r2 square minus r1 square. This is what the final energy, sorry, the change in energy that is given by the external force. This is the work done by the external agency. Okay. I have done this question using work power energy. To do it with Newton's laws of motion, I have to consider the frame as this rod, okay, this rotating rod. And if I consider that, I have to include the fictitious forces of Coriolis's force, centrifugal force, and in that method too, we can obtain the same answer. Thank you for watching this video. Do comment your suggestions and doubts. We are here to solve it. We will be uploading the PDF of these questions. We have already uploaded for kinematics, Newton's laws of motion. Now for work power energy also we will upload it. Do solve it and comment your doubts. We are ready to solve it.